Today, for those of you who are well-versed in color theory, this is going to be a bit of a snore. It is Color Theory 101. What we're going to get into today is kind of the core color theory stuff we care about as digital artists. Now, this is where some of the things might start to differ, is we're diving into the realm of digital art, and digital works a little bit different than analog. So a lot of the stuff that's in the book, for example, that is paired with this course is analog. So we'll be covering the digital side in class. So that is going to be kind of our core focus today, is to kind of give you guys a base overview of color theory, what the broad categories are, how they're used, core terminology, and all that good stuff. So as we move forward here, you have a full understanding of what we're discussing. So let's go ahead and dive in and first start by talking about what color is in digital art. Sounds funny, but it's important to understand that color in digital art is math. It is a math space. We're on computers, so it's working in that spectrum. Now, what is unique about that? Not only is it based on math, but the way we're viewing it is it's essentially being beamed into our eyes. In digital art, color is created by light and not pigment. And this is the reason why I mentioned old color theory books that are analog. They're going to be talking about pigment. They're not going to be talking about light. So digital color is a little bit different. When we talk about screens, screens actually emit light, and that makes them what we call an additive color spectrum. This is different from how we perceive color in the real world, or how do I say in the real world, but in printed medium, simply because when we're looking at it, a painting, what's happening is it's not a emission of light. It is an absorption of light. What's happening is the light is being subtracted. And this is why colors differ on screens than they do on pigment, which is an important thing to understand. So let's go ahead and talk a bit about that in terms of how this all kind of comes together. When we're talking about digital art, it's a mixture of light together. When we're dealing with the mixture of light, it actually has a different color wheel. It has a red, green, blue color wheel. So when we talk about the primary colors in digital space, it's going to be R, G, and B. These are the primary colors. This is different than printed. Printed is going to be red, yellow, blue. So the main difference here is that we've switched green in. So be aware of that. That's one of the major differences between traditional color theory and digital art. All right. When we talk about traditional, it's about mixing pigments. Key takeaway: screens glow, printed colors rely on things like reflection. So when it comes to screens, they're backlit and they deal with RGB. When it comes to print, it deals reflected light and it deals with CMYK. Now, we actually do end up working with both of these spectrums inside of digital art, which is kind of worth noting. When it comes to the RGB spectrum, that's going to be for screens, anything you see on a screen, animation, video games, augmented reality, virtual reality. So if it's on a screen, it's RGB. And generally speaking, we end up with brighter and higher values. Now, why is that significant? Because sometimes we're also working in the realm of print. Print uses a different color model, which is the CMYK color model. And that's going to be what's used for print, and it's darker with more ink applied. So what's the significance there? We can't just take something we make in RGB and print it. There's going to be a discrepancy because of how things operate. So let's go ahead and take a look at that real quick so you guys can understand this a little bit better. I'll use this image since we're on here, and we'll use this as kind of our victim for today. So let's first start out by talking about the primary colors and what exactly makes a primary color a primary color. So a primary color is a color within a system which cannot be created by mixing any two other colors. So the primary colors that we often are talking about is going to be the red, yellow, blue spectrum here. And this is going to be for things like paint or pigment mixing. And you can think of this as kind of the traditional method of color theory. The one we use for digital is going to be the red, green, and blue, and this is going to be the light spectrum. Now, notice I didn't say that's the digital spectrum. If any of you have ever worked in something like theater, you're already well aware of this, but if you're working as an actual lighting artist for photography or for stage lighting, you're already aware of the red, green, blue light spectrum and how lights mix. So it's not exclusive to digital, but it is heavily in digital because it's going to be dealing with screens, because screens are basically just giant lights. And then we have the CMYK spectrum. This is for print, and it is a newer model of the red, yellow, blue. So this is the 2.0 model. Now, when did CMYK come about and why? Cyan, magenta, and yellow came largely due to global trade and science. We created brighter synthetic light-fast pigments than we could create in nature through things like science and through materials that were, gathered from different parts of the world. So long story short, red, yellow, blue has a long history, but it was limited to the locality of those regions. And what's kind of fascinating about art history, and we'll talk about this later, is depending on what part of the world you were in, you may not even have access to a particular pigment color, which is kind of neat. CMYK's, a more modern version, and it's what's used in printing. So the red, yellow, blue is not completely obsolete, but it is pretty much completely obsolete for us as digital artists. Now, what's important to understand about these are different color models. And when we talk about this idea of kind of a color model, what we're talking about is math. And that is the base idea. Now, I'll explain this a bit more in a moment here, but it's important to understand when you're working in an application like Photoshop, you can actually switch your color mode, and it switches the math being applied and the math you can access. So one of the things I mentioned in the PowerPoint slide here is that red, green, and blue deals with light, which means that we can get really bright with it. And I accidentally went over the brightest part of the scene, but if you look at the sun or the little fire beacon here, you'll see these are both bright. The challenge with CMYK, or print, is that it is subtractive, meaning that white is the brightest thing you can have, and you can only take away from that. Now, this can be mitigated by printing on different types of materials like metals, where you might be able to bring some of that back in, but for the most part, you're going to see a loss. Now, we can see this in action in Photoshop by coming up here to Image, Mode, and then switching this from RGB to CMYK. And if I go ahead and click this and we hit OK, we should see the colors become a little bit different here than they were originally. And if I hit Control Z, we might be able to see that change. Now, there wasn't a big change, which is worth noting, so that's nice. If I did want to show you guys a bigger change, what I would do is I would boost the vibrance of this. So let me go ahead and find the tool for that. Color and vibrance. We'd go ahead and boost the vibrance here, and we might go ahead and boost the saturation a smidge. And I might duplicate that. And then go ahead and throw on a brightness and contrast here. And boost the brightness a bit. Cool. So something like this here, this is very likely something that exists only in the digital realm. Vibrance is a very weird term. It basically means the brightness of a color. It's similar to saturation, but it deals with more of the luminance value, and it's kind of exclusive to RGB. If I switch this now to something like CMYK, we should see a more dramatic shift. And you probably saw that. If I go ahead and make this big screen and hit undo, you can see how this is much more bright and vibrant, and the colors are really saturated. And when we switch that CMYK, that's all kind of getting lost here. And it's getting dampened down. As a matter of fact, this area here in the sky, the values are getting clamped. You'll see how we can distinguish these clouds here in the RGB. That's because those are pushing into the realm of luminance, meaning that they are literally as bright as the sky is. They are emitting light. And when I come in here to the CMYK, those can no longer emit light, so they hit the max brightness and they disappear. Now, it's interesting how this color math pans out. So when we take a look at digital color channels here, If I pull up my, color picker, you're going to see that we have red, green, and blue here and a value. Now, this value runs 0 to 255, and this is the mathematical space that things operate at. 0, 0, 0 is going to be black with 255, 255, 255 being white, and everything in between is going to give us the range of colors. Now, this comes from, kind of Isaac Newton's theory of light and all that fun stuff. If you look up, Isaac Newton's prism, what happened is Isaac Newton essentially shined a beam of white light into a prism, and then out of that prism came the rainbow. So mathematically speaking, all colored light comes from white. And that's the idea behind this 0 to 255 channel, is white represents the mathematical range of, capping the color, I guess you could say. And different values add up to that. So if I come in here to something like a green, for example, pure green here, pure green is going to be 0, 255 green, 0 blue, right? That's going to be the math structure here for green. If I go ahead and create a green dot here, that now has that math structure applied. Let me go ahead and apply this with a nice hard round brush. But let's say I create another layer here of something like pure red. Pure red's going to have 255 red, 0 green, 0 blue, and I'll overlap these slightly. We can then perform mathematics between these, and that's the core foundation of what we call blending modes. So blending modes, which you guys may have seen before in Photoshop, is literally just math. Now, depending on how we want this math to math, it will give us a different response. Something to be conscious of is my background is currently gray, so it is a neutral color. So it will math on top of this, but it will also math on top of the overlap. Now, when we talk about a color space such as RGB or light, what we are talking about is additive. So if we use an additive model within our math here, what we're going to see predictably is what happens to these if they were light shined on top of each other. So for example, if I set this to an additive model of something like a linear dodge add, you'll see that when red light overlaps green light, it produces yellow. Now, secondary colors are going to be colors created by mixing primary colors. So this is a secondary color of the RGB model. We can complete the RGB model pretty simply by coming in here and adding another dot here of pure blue. If I go ahead and set this to 0, set this to 255, add a green dot here on another, or blue dot on another layer, and we set this to a linear dodge add, what you'll see happen here is we get the next set of secondary colors, which is going to be cyan and magenta. So over here, you can see that we have our RGB model at work. So with RGB, what I've done is I switched this background to black, or what we might consider darkness, right? For example, your room, when you turn off all the lights, it's complete black. When you turn on a light, you see something. This is kind of the base it operates from. 0 is what we would consider our base, and then what we do is we add to it. And that's what you see going on up here in the additive RGB model. Now, you might notice I've added a white slot over here, because in the white slot, what I wanted to show you guys is the cyan, magenta, yellow, and how that works. Now, there's multiple math spaces that we operate inside of here, one of which we've talked about is the hue, saturation, brightness. We talked about that on Monday, but we just looked at RGB. We also have CMYK here, and you can see it works in percentages. Now, as you might have guessed, if we go ahead and set this to 100 over here, it will give us 100 on cyan, and I can go ahead and make a cyan colored dot. Then I could go ahead and create another layer here, and we could go ahead and switch this to have 100 on magenta. And then we could go ahead and do the same thing here to have 100 on yellow. Now, this is where things get kind of interesting, because we need to talk about the math that this space is going to operate in. We know that an additive spectrum is going to be what we use over here within our digital realm. So we use a, add. And the idea is we start with black, which equals 0, and anything we add to black is going to kind of boost that. Now, this is a little bit awkward, because when we get over to this other side here, we're starting with white. So we need to work with some sort of a subtractive space. And this is where things get kind of tricky because we're starting with 255, or what we might convey as 100%, and we're taking away from that. Now, this is the tricky part to pay attention to, though, is not the 255, but the 100%. Remember when I used CMYK, it was a percent-based value? That's because the mathematical operator that we use for this isn't necessarily a subtraction, but rather a multiplication. Now, this is a little bit hard to understand simply because you need to have a little bit of insight into how mathematics work. But when I say 0 to 255, this is the same thing as 0 to 100%, which can also mean the same thing as 0 to 1. And when you think of this as 0 to 1, think of the decimal system. 0.1, for example, is 10%. 0.5 is 50%. So 1 is equal to 100. Now, these can be represented as percentages across the CMYK spectrum. So when we do a subtractive model, or we want to take away when we are doing color mixing, we use multiply because when we take anything multiplied by 1, it's going to be equal to itself. But on the other hand, if we take fractionary information, for example, 0.5 times 1, it's going to be equal to 0.5. So it gives us the ability to kind of reduce down from 1. Weird, but let's go ahead and see it in action. If I go ahead and set this to a multiply, you will see that that now blends over the top and we get the secondaries of these colors. And I'll set each of these to multiply for us to see that. If only they were in order. Let's see. Ow, I did these two on the same layer, darn it. All right, let me go ahead and delete that layer real quick and put this on another layer here so we can see that. But you can see as those multiply on top, they are going to take on that color. Oops. That's the one I'm looking for. With 0. There we go. And multiply. All right, so that is going to give us the CMYK spectrum over there. So with the CMYK spectrum, you can see it's a bit different. What's going on over here is we're starting with white, and you can think of this as representing a piece of printer paper, right? That is the idea here. It's a piece of paper, and rather than adding to it, we are subtracting from it. But remember, we're not subtracting in the normal sense because we're doing so through multiplication, and the way that is working is by percentages or fractions, however you want to kind of interpret that, right? But that's the math operation that is happening there. Now, that's going to be the difference between how those things mix, additive and subtractive. Now, where does this come into play in other areas? It comes into play in other areas when we're working in an area like 3D. So let's take a look at that real quick, and then we'll go ahead and move on from it. But I want to make sure you all have a very thorough understanding of why this matters and how it impacts things. Because at a surface level, it's kind of easy to understand. You know, it's like, oh yeah, that makes sense. Subtractive, additive, blah, blah, blah. But understanding where they manifest, that's where the tricky part comes in. So let me go ahead and create a scene for us here. And then we'll go ahead and create some different elements within this scene. And if you guys haven't had 3D, don't worry about it. We're not necessarily using 3D in this class. I'll pull it in every now and then. All right, so let's go ahead and turn on the lights, aka turn off the lights, because when you turn on lights in Maya, they disappear. You guys can turn on lights with light bulb in Maya if you guys do want to play around with this. And I'm going to use a simple spotlight here to just pull this up here and shine it downwards 90 degrees, like so, or negative 90. Thank you, spotlight. Going in the wrong direction. And let's go ahead and just create a little scene here where we basically recreate what we just did in Photoshop with our red, greens, and blues. You'll see as I duplicate this light, where lights overlap, they get brighter. So lights innately are additive. If you shine one light on another light, it adds to it and it gets brighter. Now, the other thing to be aware of is the colors of light. If I come in here and I set one color to red, I set another color light here to green, and a final color here to blue, you'll notice just like with our original image in Photoshop, these are all adding together to create the same CMYK spectrum. Now let me go ahead and just change this to be pure white here so we can see it a little bit better, and I'll go ahead and isolate these so you can see the effect those are having. So you can see that additive light still happens here, just like it does inside of Photoshop. So why am I showing it you in Maya? Why do I have all these objects here? The reason why I have these objects here is because this light is also subtractive in terms of how it strikes a surface. For example, if I go and assign a new material to this, and I change this to be a color such as green, you might notice it runs into a bit of an issue here where it just looks green. It's actually not picking up the other colors at all. And I could do the same thing by making this red here. I could assign a new material here, and I could make this completely red. And you might notice, hey, that kind of looks black. And then we'll go ahead and assign a new material here. And we're going to go ahead and make that blue. And hey, it's actually blue. Now, if I turn off the lights, you'll notice this looks a lot different than it does with the lights. So what is going on here? What is going on here is color math, and that is where we need to understand this as a digital artist. Because if you get your color math wrong, you're going to run into some big issues. Now, what is the color math here? Well, I showed you guys that this light is 0, 0, 0, 255 to represent green, and this one's going to be 0, 255, 0 to represent blue, and this one's going to be 255, 0, 0 to represent red. Now, when those add together, it's not a problem because at the center here, this small space here we have is going to be equal to white, which is going to be 255, 255, 255. Now, in terms of color math, what's happening there? Well, if I go ahead and move these lights around and hope Maya doesn't crash on me, and I put any of these objects at the center of this collection here, you'll see the true colors revealed. So we can see that's actually red, this is actually blue, that's actually green. But you'll notice when these go into the color of light they aren't, they turn black. So the two objects that aren't blue go black there, the two objects that aren't green go black there, and the two objects that aren't red go black there. So why is that? It has to do with how math is working here. Remember, when light strikes a surface here, it turns into a multiplier. So if I have a red object here, which is represented as 255 red, or what we might consider 1, 0 blue, and 0 green, and I multiply this by a light source that is 0 red, 255 blue, and 0 green, and we just do the cross multiplication here, 255 times 0 equals 0, 250 times 0 equals 0, and 0 times 0 equals 0. 0, 0, 0 is black. And that is what I'm talking about with color math. The reason why these objects turn black in the light they are not is because we're literally multiplying 0 onto the surface in that channel. So the question is, how do we avoid this? And the way we avoid this mathematical issue, either in Maya or in something like Photoshop with blending modes, is to make sure that our color channels always have variant values. In other words, you should never use pure black, pure white, pure green if you can get away with it, pure red, pure blue. Anytime you have 25500, this is going to cause problems. And it's because that math system, because this is essentially the same thing as 100%, 0%, 0%. And when you bring that into multiplication or even addition, you end up with really wonky results. So let's go ahead and fix this within an instant here by just slightly adjusting the lights. Instead of having this light as a pure green here, I can pull this in slightly. It doesn't even need to go in that far. And all of a sudden, if we take a look at the RGB values, rather than having this set to 0 on these channels, we gain 23 in red, 23 in green, and blue. And I could do the same thing here with the blue, just bring it back slightly. Same thing here in red, just bring it back slightly. And if I do this now, you'll see that these objects never go black anymore. They will darken, but they never go to full black. They always retain some semblance of their original coloring values. Now, how can I make this even better? Well, we do the same thing with the objects. Rather than the object being 255 red, we just give it a slightly less saturated red. Same with green. Rather than making it pure green, we give it a slightly desaturated green. And with blue, we give it a slightly desaturated blue here. And now with those having a better mathematical space to operate in, as I move this around, we'll see that, these are going to show as their true color a little bit better no matter what light it's under. Now, some light can't be helped here, but hopefully that kind of helps you understand. So that is a very in-depth look at additive and subtractive models within the digital realm and how they affect digital art. So hopefully that kind of helps you understand how these come together and how they operate, within the art that we're creating here. All right. What's important to understand, though, is we're generally going to be working in RGB. That's going to be kind of our final output. But there still are systems where subtractive comes into play. For example, when light strikes a surface in 3D, or when we're trying to work in print specifically. All right, so let's get into, the meat and potatoes of this a little bit more. We kind of have an idea here of when each color, models it matters. In general, like I mentioned, we're going to be working in RGB for digital. CMYK is more exclusive when you are preparing work for print. And generally speaking, we don't work in CMYK, we output in CMYK. So it's a lot easier to work in RGB. And then finally, when you're ready to export, you go in CMYK. But it really depends on the workflow and the industry you guys end up with. So now that we've gotten that out of the way, let's go ahead and talk about the color wheel, its purpose, and all that good stuff. When we talk about the color wheel, its main purpose is to organize hues by relationship. And it gives us this idea of secondary, primary, and tertiary colors. And I said that in the wrong order accidentally, but you guys get the point. Now, we already kind of talked about this idea of primary colors. These are colors that can't be made by any other colors, so they can't be made by mixing. And once again, this depends on your model. It doesn't, there's no strict rule. That's an important thing to understand. It just depends on the math. So if you're in the traditional model, that's going to be red, yellow, blue. If you're in the digital model, that's going to be red, green, blue. If you're in the print model, that's going to be cyan, magenta, and yellow. So those are going to be our primary colors. Now, when we talk about secondary colors, these are colors made by mixing the primaries directly. So for example, if I mix red and green in the RGB spectrum, that's going to be equal to yellow. And that's something that we saw. Likewise, if you mix green and blue, that's going to be equal to cyan. And if you mix red and blue, that's going to be equal to magenta. Now, how do I memorize that? It's pretty easy. Red, green, blue, and CMYK are opposites. So when you mix red, green, and blue together, you get CMY. When you mix CMY, you get RGB. And hopefully that's something you guys noticed from the Photoshop demo here. If you didn't, you guys can see it here. I can't remember if I pointed it out, but you'll see those secondary colors are present here and here with this one here. Now, that brings us into the other one, which are the tertiary colors. Tertiary colors are everything in between. So these end up having abstract names, but things like blue-green or orange-red, they generally are hyphenated, but it's kind of worth noting what they are. Now, what's important to understand is these tend to be used for understanding of relationships. They're not really strict rules we follow, but it also is being used for predictability. If I'm going to add a little bit of this color over this color with this mathematic, you can kind of predict what it's going to produce. So for example, if we take a look at our diagram here, let's say I have, some sort of a surface here that's blue, and I decide I'm going to multiply yellow light over the top. Well, it's not going to be yellow light anymore. It's going to turn to green from the mathematics. So we can kind of predict what happens there. Now, let's get into the important elements of color. We touched base on these previously in the last lecture. They're going to kind of form the core foundation, and they're going to be what we kind of explore most in depth this week. So we talked about hue last lecture, and that describes the color something is. What's important to understand is that changing the hue can alter the mood or meaning of a piece. So on the side of the screen here, I have this demo image, and you can see on one side we have a somewhat monochromatic hue of oranges and yellows, and it feels very rich and warm and like a sunset. And then on the opposite side, we have a hue that has kind of been shifted from orange and yellows to blues and purples. And we get this sort of almost haunting majestic night scene. Both have a very different feel, and all that we've done in this image is change the hue that is present. Now, what's important to understand is that's something that is completely doable in the digital world in post-processing. You may already be aware of this, but we do have tools that allow us to do this. Now, we're going to be using this much more heavily But just to kind of bring in a example here, if I come into something like the adjustments here and I use the hue and saturation blending mode, I can actually isolate the hue here and we can shift the hue of this piece to be whatever we want. Now, with that said, it's going to work better with certain hues over others, but you can see we have the ability to just shift the hue here, which drastically changes the mood of the piece. And once again, we're not changing anything but the hue, which is also kind of a problem because I could probably benefit from some other adjustments to make this look a lot better. But that's the base idea behind hue there. Now, when it comes to shifting the hue, small hue shifts can dramatically change the tone of a piece. By making it, slightly warmer, slightly cooler, it completely changes the effect and the emotion behind the piece. And you can see that here in this example. The yellow one has this very warm feel to it, whereas the blue one has this very colder feel to it and almost makes it feel like a haunted castle, whereas the orange one, makes it feel more like a sought-after destination, I guess you could say. The next category is going to be saturation, and saturation describes the intensity of the color, in some ways how bright it is as well. What's important to understand is that high saturation draws attention. Now, I have two examples down here in the corner, one highly saturated image, which is our image with the orange background, and one lower saturated image. Notice in the high saturated image, it's so saturated that color and saturation doesn't really guide our eye that well. And this is an important distinction to understand about how these can utilize. Whereas the lower saturated image, because our character here actually has saturation on his little staff here, that actually draws our eye quite substantially because it's the most saturated thing in the image. So this gives it a bit more visual weight than his staff over here, which basically blends in. So something to kind of be cautious of is that saturation is going to really kind of affect where we look and why. Now, what's significant about this is that oversaturating something can cause problems. When we have too much saturation, it causes visual noise. We don't really know where to look. It has no real focal point, and it can cause eye fatigue. So on one of these images, I've kept kind of our original orange one here, and then on the other one, we have kind of this bedazzled rainbow spectrum of hue and saturation. And you can see in that one, it's a bit more chaotic, and the eye doesn't settle as easily as it does on the first image. With the first image, our eye is very easily drawn to the character and to the main castle here, and that's because the saturation is much more well balanced than it is in the second image. In the second image, we still are drawn to the character, but then the landscape kind of becomes a hot mess because the sky has so much saturation and the mountains do, that this almost becomes the next focal point, this valley here that's beyond the castle, because it's the least saturated thing in the piece. So it's important to understand that saturation is going to be one of our key tools in guiding the eye. Now, with that said, why does the first version of this image work and not the second? It works because of value. Hue, saturation, value are three pillars that we balance an image on. And even though an image's saturation might be completely off or may not be guiding the eye correctly, you can still guide it through value, through contrast. So what this first image has that this second one doesn't have as well is we have a very high contrast between the subject and the castle, and that's getting a little bit lost here because this hue is so bright. So getting into value, value is going to be how we achieve contrast, and it's going to describe the relative lightness or darkness of an image. So over on the side here, we have a low contrast version and a high contrast version. And you can see the low contrast version seems a bit washed out, whereas the high contrast version seems perfectly fine and looks quite appealing. And that's because value is going to be what controls readability. It's going to be what makes an image instantly able to read, which is very significant. This character is kind of starting to blend into the surroundings a little bit too much at this value, but with this darker value, it stands out clearly, as does the background. Now, this comes a bit into biology, which is worth kind of noting, and into our eyes and how eyes are set up. Eyes have different types of cells in them. They have cones and they have rods. When we talk about the different cells in eyes, cones are going to be what lets us see color, and the only reason I remember that is because cone starts with a C and color starts with a C. And rods are going to be what lets us see value, and it's important to understand that these are different from each other. What's also important to understand when it comes to the human eye is as light enters, it strikes the back of our eye where these cells live, and we actually have more rods than we have cones. This is because color is an evolved mechanism. Not every animal on this planet actually sees in color, and if they do, they don't see in the same color spectrum we do. Most animals can't see the color red, for example. A lot of them just see in blues and greens. So what's important to understand about this is in terms of our biology and in terms of how we actually visualize things, value matters a lot more than hue. When it comes to art, a lot of the times we will look at it in grayscale, and we'll talk more about this as we move throughout the course, but desaturating an image is one of the easiest ways to find the problems with it, because color can be very deceptive. Color has three factors to it. It has hue, saturation, and value. But it also has kind of a hidden multiplier in digital space, which is called luminance, and that's how relatively bright it looks to the surrounding, which has nothing to do with value. In short, you can perceive a color like yellow as extremely bright when we see it in color, but then when we desaturate it, you might actually find it's a darker gray value, and that's because the luminance value of it is making it appear brighter. So there's a general rule of thumb we have in art, which is if it works in value, the color is usually going to work as well. When we remove the color, it reveals that value structure. We can use this to diagnose problems and figure out how to correct our image. Generally speaking, good value is going to be what supports composition. And that's because the key to composition, composition meaning the layout of a shot, is contrast. Having the correct contrast is really going to kind of push the image in the right direction. Now, this image is actually an excellent one for the desaturation process, because when I take away the color, look at how flat the sky goes. So this is an image generated by AI, so big surprise. However, the desaturation is not. I desaturated the image and manually put them side by side, and this is part of the reason why I like to call out AI, because AI is not the most amazing artist. As an artist, if you were working on this piece and you put this into grayscale and you saw how flat that sky looked, you would fix it. So in short, this is actually not the best piece of art. The contrast is way off here, the value is way off here, and they really do need to be pushed. What's working best is kind of the foreground contrast of the subject to the background, but once you get to the background there should be a lot more lighter values in those clouds, as opposed to just using color to make them stand out. Now, just to kind of show you guys the process of grayscaling something, you can actually do that here with the hue saturation slider, no problem. You just pull the saturation down to 0 and you can see the impact that has on the image. Now, this is a little bit different because we are just taking saturation away. There is also black and white, which does kind of the same thing, right? So you can see both of these will give you a grayscale. It doesn't look as problematic here, so I'm wondering if I used a different image than this one to grayscale it out, or if maybe it just looks bad downscaled. But you can see how an image reads in terms of contrast from just doing that, right? So you can get an idea of what's good and what areas could be, revisited. A great example here, though, is this area here. Notice how bright these areas look compared to the surrounding area. Yet when we, lay these side by side, you'll notice that they are not nearly as bright as it appears. And if I go ahead and do a fun little exercise here where I just sample, this red here, make a big brush, and this black, so you can really see that, you'll notice that looks a lot brighter than that. But when I desaturate them, they don't look quite like the same brightness you would imagine, right? That looks a lot closer to that than, you would have thought. And that's what I'm talking about with that idea of vibrance. It's different than saturation and value in the regards that it's, how the color actually reads to the eye versus how it's mathematically formed. Colors can be more vibrant than mathematically visual. I don't know the proper term there. But that's going to be why value matters more than any of these other subjects. And we'll come back to this again later in the term, but just kind of be mindful, value is going to be really the base foundation you want to start with. Now, one of the things we're going to discuss kind of solely in its own week is this idea of color harmonies. When we talk about color harmonies, these are color sets that work well together, and they're generally based on the color wheel. Examples are going to be things like analogous. When we talk about analogous colors, those are going to be 3 colors next to each other on the color wheel. And when I talk about the color wheel, this can be any color wheel. I want to emphasize this. Generally speaking, we equate it to the red, yellow, blue color wheel. That's the one we traditionally use in terms of mathematical in terms of traditional art mixing. But there's no reason you can't use the red, green, blue color wheel. Now, what are the big differences? In the red, green, blue color wheel, things like red are going to be opposite cyan, whereas red is going to be opposite green in your traditional color wheel. Either work. That's the cool trick, if I'm going to be honest. And once again, it has to do with mathematical models of how we perceive light. It's not to say that you can just pick any colors and they're going to work well together. It's pretty close to that, if I'm going to be honest. So analogous colors are going to be colors next to each other on the color wheel. And in this particular one, that's basically using a combination of blues and greens. Complementary colors are going to be colors opposite on the color wheel. And this is excellent if you want to get maximum contrast through color. Now, notice I'm saying contrast through color because the other contrasts show differently. For example, you could have contrast through saturation. We looked at that earlier with the character's staff being more saturated than the rest of the piece. And you can have contrast through value, which we already see with the character and the building in the background. When we do contrast with color, you'll see that the green section of this area helps emphasize the various red beads. So the character's staff and the reflection of red light off him is kind of drawn to, and the castle is now drawn to where we get this main focus. The final one that I have an example of here is going to be triadic, and triadic colors are going to be colors evenly spaced on the color wheel. This is using a red, yellow, blue color scheme. It's very hard to pull off, but very dynamic when achieved correctly. Now, how well they're being achieved here, I can't really say. They're all kind of in the middle. But hopefully it kind of gives you an idea of how a single image can be recolored a number of different ways to have a very different effect and different impact. We're going to be exploring these more in depth later in the course, so if this is not a good enough explanation, don't worry, we're going to get into it. But the main thing to take away with color harmonies is they are color sets that work well together based on the color wheel. All right, now another thing to discuss is going to be color and focus. So when we talk about color and focus, we can use it to kind of guide the viewer's eyes. I talked a bit about this a moment ago, but contrast is going to be what allows us to direct attention. It's going to let the audience know where to look in a particular piece. And you can contrast either color, which you might think of as hue, and that's what I talked about with the idea of complementary color, and we see that in the first panel here, where you have your reds and your greens being contrasted against each other. You can contrast value, that's going to be darks and lights, and you can see that in the second panel, where you have the dark character in the foreground, the light staff kind of as a focal point to see that they're a magician, and then as that recedes into the background, we have the contrast between the very bright moon being behind the castle. So that makes the castle a focal point because we have a light-dark contrast, and it makes the character a focal point because we have a light-dark contrast. And then lastly, saturation. You know, how saturated something is going to help push the focal point. Now, in this particular image, I feel like my example is probably not the best, but you'll notice that I have pushed the saturation on the magical staff to be a bit brighter than the rest of the scene, so that that magical staff doesn't just get washed out. We still see that there is some sort of a magic bauble there, and it draws our attention a little bit more. Now, what's important to understand out of this is that value contrast is by far the most important. If your value is not working, your image is not working. So we'll talk about that momentarily, but that's the one thing these all have in common is at a base level, their value is contrasting perfectly. Contrasting color on top just helps with further emphasis, same with saturation. But if your values aren't contrasting correctly, you're not going to have a good piece of art. So there are a lot of beginner mistakes you guys can run into. One of the big ones is going to be same value everywhere. This is obviously a very dramatic example, but this first image here, what I've done is I've removed the contrast of value and I've replaced it strictly with contrast of color. And you can see that it still works. We can still distinguish our character from the background there, but it's not good. It doesn't look good, right? So that's what I mean by you can't just carry a piece with color alone. You really need to make sure that the value is working. And it doesn't matter if it's a digital illustration, a 3D rendering, a website layout, a pamphlet, a flyer. If the value's not working, you're going to have an issue. So make sure that you have separation and value or it's not going to read. Another big factor is max saturation, and that's what you see in the second one there. Max saturation causes something called posterization, and that's where the edges of one area basically collide into another. And you can see that here with these clouds, how they're no longer flowing smoothly from one area to another. They're kind of clashing and, not blending nicely. So you want to avoid, maximum saturation. It's kind of overwhelming and the color math just doesn't work. And then the next one's going to be too many hues. So we talked about this idea of color harmonies. Color harmonies is picking a handful of hues to work with and then utilizing those across the piece. You can make something whimsical and fun with this rainbow effect, but after a while, if you're going to watch an entire movie or play an entire game that has this rainbow effect applied, you're going to get annoyed because it doesn't really help guide the focal point. It doesn't guide the story. It doesn't help with emphasis. It turns into just kind of color vomit that's not terribly appealing. So we generally want to work with some limitations there when it comes to the amount of hues we use. Okay, now what was the purpose of this entire lecture? It was to give you a very strong foundation of understanding the idea of color models, color math, but also to help build your vocabulary of things like hue, saturation, value, contrast, color harmonies, color models, all those things. So when it comes about talking to color choices, you really want to avoid things like I don't like it or this feels off, things that are very vague. You want to discuss them in actionable terms. And the way we do that is by talking about how images are built. We talk using value, saturation, and hue, and other color theory terminologies. So it's important you kind of, get that in mind. So in this image, we have a bunch of people looking at this image. This guy doesn't get it. What he might say here is, the image looks good, the contrast feels good, but I can't help but feel that we're missing here on the hue. It's monochromatic. I think we could really benefit from introducing something like complementary colors here to make the castle pop a little bit more and the character pop a little bit more, right? So that's tangible feedback. Saying, I don't like it, or something feels off. That's not acceptable. Now, why am I talking about this? It's because when you guys get into the real world, you will collaborate with other human beings. I know it's crazy to think about, but one of the big things is going to be giving and receiving feedback. It's important to understand that you're going to get feedback just like your instructor gives you from an art director. That's literally your day-to-day job as an artist. If you guys want to know what it's like to be an artist, you work your whole day, you submit whatever progress you have made to your lead. Your next day starts out with you basically starting your day working in a certain direction, and then at some point you're either going to be pulled into a meeting with your lead, or your lead's going to send you notes on your progress and let you know if it's on track or what needs to be fixed. And the way they're going to do that is through this sort of language. So just kind of be aware of that. So really feedback is kind of the overarching term, right? In terms of how you're going to be communicating with this. So I don't really need to get too much to collaboration, but collaboration is also a factor, being aware of different workflows. For example, the fact that starting with good value, it really kind of sets the foundation for the entire project. So, when you're doing your blockouts or your planning, planning value first can be very beneficial. So there's a lot of, different elements when it comes to collaboration. And that ties also into efficiency, knowing that contrast is one of, if not the biggest thing you need to get right. You'll know to aim to get that right initially to make it as efficient as possible. So that's, where this terminology comes into play. So is it important to learn this stuff? Is it important to memorize this stuff? Absolutely. I can't emphasize it enough. If there's any of these areas that you're feeling a little bit iffy on, you need to brush up on, it is one of those things to really kind of double down on and get the research right. Because like I mentioned, it's going to save you a lot of embarrassment when you get into the workplace. If you're just familiar with these terms, familiar with how to adjust them, familiar with what they mean, because this is generally going to be how we are communicating in this industry. All right, so that's going to wrap up the core lecture for today. Hopefully you guys found it insightful, and it gives you a base foundation kind of move forward with in this course as we progress. Like I mentioned, in future classes, we're going to really get into these topics more in depth, in particular the color harmonies. We have an entire week blocked out for that, I believe, so we will be revisiting that time and time again. But the real key things to take away from today is going to be understanding the different mathematical models, understanding that idea of additive versus subtractive, that we work in both models realistically as a digital artist in some capacity, that they come into play when we're dealing with things like blending modes, and that hue, saturation, value are kind of the three pillars that these images are going to be situated on, and they kind of interlink to create all the images that we see. Be sure to like and subscribe so you can catch the next video in the series when it goes live.